So the plan for this week, you have homework 5 due on Thursday. That's 48 hours from now. We have a couple office hour sessions between now and then, an hour after class today over in Farrell, and then tomorrow from 1:15 to 3:15 p.m. Homework 6 will go live in 48 hours, and that's the last homework before the midterm exam, take-home midterm. So you'll turn in homework 6 a week from Thursday, and then I'll give you the exam. You'll have 10, 12 days to work on it over break at your own pace, and then turn it in on the first day of class after break. There is no class a week from today. I think it's town meeting day, so that's pretty cool. All right, so we got 3 lectures left. The plan for today is to talk about a couple examples. So you've been working hard to understand this concept of the Lyapunov exponent and chaotic dynamical systems in one dimension. So today we're going to take a step back and look at some applications of that concept in measuring chaos in the solar system and on social networks. These are things that I've done some research on with people here at UVM, and I'm going to tell you a little bit about those things today. Questions about our plan? Okay, cool. So let's get going. So space. How cool is space? It's amazing. We're going to talk about chaos in the solar system. This is a problem that people have been thinking about for, since it was kind of the inspiring problem for us when we were first talking about chaos, right? Was the n-body problem that Poincaré was trying to figure out why the motions of 3 bodies was so much harder to analyze than 2. And ever since that time, people are trying to figure out whether our solar system, in fact, exhibits chaotic orbits. You look out at the sky, you see the moon's in the same place every day, pretty much. It's in this phase-locked orbit around the Earth. It's basically quasi-periodic. What about on a time scale of 1 million years, or 100 million years, or 1 billion years? The question we're trying to answer is whether or not the planets exhibit this sensitive dependence on initial conditions we've seen for these really simple nonlinear maps. Your intuition when you see the fact that it's all still here, the fact that you exist means, probably it's stable. But this is a question that people have been thinking about for a while, and I'm going to tell you a little bit about it. And I think it helps always in this class to start with a quote from Lorenz. So he's thinking at this point still about how to convey to the Weather Service that these linear methods of prediction are not going to work. This was before his big hit paper in 1963. So maximum simplification of the dynamic equations. This is before they could really use computers to integrate the motion of the Earth's atmosphere on a computer well. So I'm just going to read you a quote from Lorenz. If we should observe a hurricane, we might ask ourselves, why did this hurricane form? If we could determine the exact initial conditions at an earlier time, and if we should feed these conditions together with a program for integrating the exact equations into an electronic computer, we should in due time receive a forecast for the computer which would show the presence of a hurricane. So this is sort of, we're imagining the possibility that we had a perfect computer, we had exact knowledge of what the state of the atmosphere was like. These are things that we're not quite there yet, but we're getting there. All right? This forecast of Sandy was good about 8 days in advance for its position. Okay, so he's imagining, this is a thought experiment back in the 1960s. It was not clear that we would be able to get to where we are today back then. But so this is a thought experiment he's having. We might then still be justified in asking why the hurricane formed. The answer that the physical laws required a hurricane to form from the given antecedent conditions might not satisfy us, since we were aware of that fact even before integrating the equations. So we see the hurricane. We know it's there. We go plug it into the computer and see that the computer can produce it, but the computer's perfect to begin with. Did we learn anything? Not really. If you have a perfect model of something and it's just handed down from you, and that's what a lot of these machine learning techniques are giving us now for things other than physical systems. They're not perfect, but they're getting good at predicting. What have you learned from that process? Not very much. And so he goes on to talk about what it means to be in this situation. It's only when we use systematically imperfect equations or initial conditions. So you make the model worse. You go in and fool around with the parameters or change the initial conditions a little bit. that we begin to gain further understanding of the phenomenon. For if we omit the terms representing specified physical processes, such as friction, from the equations, or if we fail to include certain observable features, like cloudiness in the initial conditions, we may, by comparing the mathematical solutions with reality, which will be wrong. Right now, the forecasts are going to move away from reality, because we've changed the model. We may, by comparing the solutions, gain some insight concerning the relative importance of the retained and omitted features. Of course, in doing so, we forego the opportunity of simultaneously making the best attainable forecast. So this is, he's thinking back in 1960 about this idea that we're now learning about, where you look at an interval around your best measured state of a system, and you ask the question not just what do the equations predict that the best guess will do, but rather you get an uncertainty prediction from what that interval does. So what are the perturbations of the best guess within known uncertainties? What do the forecasts say those things are going to do? And the rate at which that grows, that gives us some confidence interval then in how long we can make a good forecast. So perfect model, not really useful, but when you go in and mess with it and you see that you can turn this knob way all over the place, you get the same answer, okay, that thing doesn't matter very much. And as you're learning in this class, there are some parameters that really do matter and some initial conditions that really matter. All right. So I was at Maryland working on this weather prediction problem, and sometimes I like to show these videos that we have now of like pictures that have been taken by the robots we send into space. This is a particularly good one. So I'm going to play this. Get the mood music going too, that's always nice. These are pictures taken by one of the satellites. It's almost a decade old now, but they're like IMAX resolution pictures. They're stitched together like it's a movie. It's not a movie. The pictures are just being stapled together. So they're stitching together lots of pictures there. We don't get to go out and observe this ourselves, but we can send these cameras out there. They take these pictures. These are real pictures being sent back. This is incredible to me. These rings are in some places only about 10 or 20 feet thick, rock and ice. Like, you know, you think you're in one of these movies, right, where they're going to send astronauts out. They're not movies. These are just pictures, and they're real. That's crazy. Trying to figure out whether there's water on some of these, some of these moons of Saturn and Jupiter. We're also trying to figure out whether there's life on planets around other stars. And the way they often do that is by looking at transits. So when a planet passes between one of our cameras and another star, you can observe the dip in intensity that's very regular and infer the mass and the distance from the star when that happens. And the idea is that you could look at what elements are being absorbed by the light coming from that distant star as it goes through the atmosphere of the planet orbiting that star. So in 2012, when Venus passed in front of the sun with respect to some of our satellites to take pictures, they were performing this experiment. Can we look and infer from the atmosphere of Venus which elements are present in the atmosphere? Because if we can do that really well when Venus is, very nearby compared to these other planets, And we might be able to figure out whether there's life on planets, many, many light years away by looking at the chemical composition of the atmosphere on those planets as observed through the star that's behind them. So they have lots of fancy instruments to measure, different wavelengths of light. These are different views stitched together. The sun's incredible, also obviously. Lots going on. So you can imagine the little bit, just the little atmosphere of Venus, what you could measure about. Here they're occluding it all; it's just this black circle. But they can get measurements of what elements are being absorbed. So that's an amazing question. Is there life on planets far away? These are, the mood music is just to get you ready for the exciting discussion of chaos now. So, so we have these great observations of other planets, and I'm going to talk about maybe a little less exciting but more fundamental problem related to the material you're learning in this class, and that's just predicting where the planets are going to be. We already talked early in the semester about the idea that we might want to know why the planets are where they are now and be able to answer questions about the history of our solar system based on what they look like. So let me get the lighting here. So, we observe them to be in particular places and distances from the sun, and can we decide using a numerical model how the solar system formed based on their distribution now? And that's a question that people have been trying to answer. And then that's a more complicated question. But the one that I'm going to talk about today that I've done a little work on is trying to figure out whether their orbits are chaotic over long periods of time. In the definition of chaos that we know, from a week ago, where we're talking about, the orbits appear to be bounded, and they're not, hopefully not, if they're going to be chaotic, approaching something that repeats. So a perfect elliptical orbit would be, we don't want to be approaching something like that if if we're going to have the orbit be chaotic. And we also want there to be a positive Lyapunov exponent. So if I go and nudge one of the planets a little bit, I would like for it not to return to where it was. I'd like it to grow exponentially in time away from that spot if the orbit of the planet is going to be chaotic. So that's the question we're talking about. This picture's each planet's to scale, but obviously they're not that close to each other. So people have been thinking about this a while. This Jacques Lescar, back in the 90s, he decided that the inner solar system is, in terms of the words that are colloquially used, outside this room, it's stable. I mean, it's here. You see it. It probably, wasn't the case that, any sort of chaotic state would have led things to be very different now since it's been around for a while. But the planets move with respect to their radius from the sun quite a bit. So these gray areas that you see here, like for example this little band around the Earth's orbit, that's how far the Earth has been thought to move over the course of 5 billion years. If you use one of these numerical models and try and figure out what the orbit has looked like over a long period of time. People are obviously really interested in this with respect to the climate. If we happen to be closer or at different angles with respect to, if the orbit of the Earth is changing, then that would have effects that we could observe in the ice cores that are dug out of Antarctica and Greenland. And people who do this sort of high-resolution numerical modeling are also involved in answering those climate questions. So this is how far away, the Earth could go here and here. Mercury is, it's got this very wide gray band. So Mercury, over the last 5 billion years, has been quite close to the sun, quite far from the sun, in fact, overlapping with Venus. Venus's band is like this, and then Mars, big band. So they move around quite a bit. Yeah, did you have a question? The thick black bar is, like for example, right here is Mercury's orbit right now. And then over the course of these last 5 billion years, it's been in this gray band.
Oh, that's the overlap with Venus and Mercury?
The overlap here is between Venus and Mercury, yeah. That's right. Other questions? Okay, practically stable. Cool. So where do these instabilities and stabilities come from? A lot of them has to do with resonances. The one that you know the best maybe is the moon. So we talked early in the semester about how there's still a discussion going on about how the moon formed. Was it hit by a bunch of different bodies or just a single Mars-sized body hitting the Earth and creating the moon? It is the case that back when things were really hot and cooling off and the moon was orbiting the Earth, that they cooled off together, which led a lot of the hot stuff to be pulled towards the Earth from the moon, the tidal forces, which led the side of the moon that faces us to be heavier, which phase-locked the moon in an orbit around the Earth where it's always facing us with the same side. So every month, the moon goes around the Earth once and goes around itself. Let me get this right. So the moon turns a single time around on its own axis at the same frequency with which it goes around the Earth. So this is why Pink Floyd named their album Dark Side of the Moon, right? If you were over on the other side, you'd see it, but you don't see that from the Earth when you're looking up at the moon. You always see the same face. So that is a resonance. The fact that every time the moon goes around the Earth once, the moon spins around its own axis once, that is a resonance with a time period of whatever, 28 days or so. So there are a lot of those in the solar system because when things are cooling off, they like to come into resonances like that. That's sort of the minimum energy state when they're done. So here are two example resonances that you could imagine coming up with over, I guess it's 12 years for this top one here. So you have, let's say you have a star, and then you have two planets. One's bigger than the other, and the planets are both going in this direction. The inner planet's going maybe twice as fast as the outer planet, so every 12 years they're back in the same place. But the outer planet's orbited once, and the inner planet's orbited twice. So that's a 2-to-1 resonance. Question about that? So that's a stable 2-to-1 resonance. There's an unstable 2-to-1 resonance down here. Unstable because when the little planet, the one that's less massive and could be ejected, when it's close to the big planet, it's farthest from the sun, and that's different than the top row. So as you imagine this resonance happening, here's the little planet coming. Here's the little planet coming around. Here's the big one. It could get pulled into the gravitational field of that bigger planet and either brought in to crash into it, spin around it, or take off more likely and leave. And so that's a resonance that you wouldn't expect to observe in the solar system because it's unstable, like our pendulum pointed straight up. So there are these different types of resonances, and there's lots of these in the solar system, and chaotic behavior can result from overlap in these resonances. So if you have a few of these things going on, or you have an asteroid that's orbiting one, a pair of planets that are in one of these, things can happen as a result of these resonances, which is what most of the planets are in. So Venus and Mercury are in, Venus goes around 9 times for every 13 that Mercury goes around, and then Earth to Venus as well. So this is a very common thing. And people have found that as a result of these overlapping resonances, the inner solar system is chaotic by the definition we've talked about. So a small perturbation of one of the states, like where the Earth is, that perturbation doesn't decay in time. It grows exponentially at a rate we can calculate. It doesn't approach asymptotically periodic orbit. And people have shown that over and over again with these numerical models. But the outer solar system, we're not really sure. And that was the question that I was trying to answer in this research project, is whether or not the gaseous planets exhibit these chaotic orbits. Okay, so often what we'll do is, that's just for scale, they're bigger, but they're far away. Okay, so often what we'll do is make these little models, like we write down the mass of the planet, and we write down its position, its distance from the sun, what its orbital radius is. And that's something that we can measure. I was showing you these videos before. We can measure that pretty well. So when the Jet Propulsion Laboratory decides to tell you, like, where is Jupiter right now? They go and look. They can give you 7 digits of accuracy in the position of its center of mass, which is basically like putting it on campus somewhere. We don't know where Jupiter's center of mass is, but to within the area the size of our campus. That's pretty good, considering that it's far away. So that's just to give you an idea of how good these measurements are. Very important to quantify the uncertainty in our initial conditions for these problems, right? Because as we know, that's how big the interval is that you're going to decide. Is it stretching or shrinking, and how quickly? So the outer solar system, because we see it, is practically stable in the sense that things are still kicking around. And here are some example simulations of where each of these bodies has been. So Uranus and Neptune sometimes switch position. That's one thing that you can see here. Their orbits are elliptical but very close to circular. And then there's this off-axis orbit. Okay, so the model that we use, the numerical model, like the logistic map, the Hanon map, the set of equations we use is just gravity, okay, the gravitational attraction between bodies. It's an n-body simulation problem, just like the one we talked about earlier in the semester, where each planet's got 3 positions and rates of change of those positions. So there's 6 numbers to quantify its state initially, and then you have its mass, and so that's it. Those are the things. The mass of the planets does not change on the time scale of the problem we're interested in. For the stars, it does. So the sun has a change in mass that's, and there are like little switches in these models for relativity if you want to include things like that, or the moons. And what we do then is we take the sun and we move it just a tiny little bit to account for the mass of the inner planets, which are just tiny little correction to the solar mass when you're thinking about what gravitational field is experienced by the gas giants. So that's what the model looks like. So it's got position and velocity for these 6 bodies, or these 5 bodies, and then so that's like 6 times 5. There's 30 numbers you're integrating in time. Some of the numbers you know really well, and some are a little bit less. 5 bodies, 3 dimensions, 2 variables. Yeah, so spatial dimensions, 2 variables, position and velocity. Okay, so that's the model that's being described in that we're going to talk about. And then we haven't talked much about differential equations, but there are lots of ways to decide how to approximate a continuous trajectory in time using discrete steps. And there's a whole class on that. Teaching some of it this fall, numerical analysis, if you're needing another math class. I'm teaching Math 237, which addresses this sort of thing. But basically, the idea is, the equations give you a rate of change of each of these variables, and you take a small time step in that direction of that rate of change to try and figure out where the planets are going to go. The time steps, like how long is that step, that little approximation in time, they're on the order of a couple days, and then we integrate this for 1 billion years. Like, where do the planets go over the next 1 billion years? And we're going to make little perturbations and see what happens. And this integrator, this is crazy. It's exact to double precision. So if you've given it, 64 bits worth of position data, and then you integrate it, 1 billion years forward in time, there's no error introduced by approximations and multiplication and division. It's one of these special ones that some of you tried to code up for the logistic map. And that's by design, because you want to preserve the significant digits that you have for a serious calculation like this. All right, so this is the sort of thing that we do when we integrate this model. This is millions of years down here, so that's 1 billion years on the x-axis, and then this is a log scale here. Here's the crazy experiment, these sibling experiments that we're going to do. We take the state of the solar system given to us by JPL. This is like what things look like right now. And we take one planet, for example, Uranus, and we perturb it by 1 millimeter. So think about that. So we're just, that is in the mantissa, this is the 52 bits of its position. We change the last bit from a 0 to a 1 or a 1 to a 0. It's the smallest perturbation we can make to the initial state on the computer. So we're taking Uranus and moving its center of mass by 1 millimeter. My hand's moved about 1 inch. Smaller than that. And then we're going to integrate those 2 initial conditions forward in time separately. They're their own universes. One where Uranus was here and one where it's here. And we're going to integrate those forward for 1 billion years and measure the rate of change of their 2 positions in this 30-dimensional space. It's not just Uranus we're going to measure. We're going to measure all the planets and all 6 of their variables. Okay, so that's the problem. And the question is, how quickly does the vector between those two states grow? It is initially of length 1 millimeter. And over time, if the planets start to do something different, the vector grows. And how quickly does it grow? If it grows polynomially, then you're going to see this thing sort of roll over. And that's a stable state, a not chaotic state. And if it grows exponentially on this plot, that's going to be a straight line. And it's not going to roll over. That is a chaotic initial condition. OK, so we're doing this sibling experiment. We perturb one of the planets by 1 millimeter, and we ask, well, how quickly does the perturbation grow? Here are some examples of what those perturbations look like. So over the course of 1 million years, it starts out really small. So this is a kilometer, and I was saying that the perturbation is a millimeter. So it's like another 10 to the minus 6 times this. So it's really tiny, and it grows quickly to begin with. But then the question is, what happens next? And like I was saying, some states might look chaotic. So this is how far apart are these two trajectories over time, and some don't. Questions about what we're doing? By the way, each of these is a different spot in the uncertainty ball of Jupiter that I was talking about. So if Jupiter's position could be anywhere on the campus, I could put it here. I could go put it over in Voti. I could go put it over by the Davis Center. That's all different initial conditions, each of which gets its own little sibling. But they're all plausible states of the solar system. So they're, like Jupiter could be anywhere on campus. I can move it around, and then everywhere I drop it, do the sibling experiment with Uranus and see how quickly does it grow. And what this picture is showing is, well, it depends where you put Jupiter, for example. Did you have a question?
Do we know how much we have to move a planet to completely eject it from the solar system?
Somebody knows that. It's not a part of my experiment, but yeah. The question was, how much do we have to move a planet to get it to leave? It's probably pretty rock solid, the answer. But that's a lot of energy. We don't have that much energy. So, questions? OK. So we're trying to answer this question, is the outer solar system chaotic? And what I was just showing you is that for different places for Jupiter, all within known uncertainty of where it is, sometimes we get chaos and sometimes we don't. Sometimes this perturbation of Uranus grows exponentially, and sometimes it grows slower than that. So that's interesting. So people worked on this doing numerical integrations of the solar system, and there's no two-body resonances in the outer planets, which was the source of chaos in the inner solar system. So nobody really knows theoretically why there should be chaotic behavior. It can be induced by taking a big time step. So there's no real analog to that in the discrete map stuff that we've been doing, aside from maybe doing single precision instead of double, things like that. So some people have found no chaos among those planets. Some people have found 3-body resonances in these outer planets. So some people have done 27th order Taylor series. So you remember the f of x plus h equals f of x plus h f prime plus h squared f double prime over 2 plus h cubed f triple prime over 3 factorial. 27 of those things to calculate what the slope of this little time step should look like. So those are really good, quadruple precision. And so time steps, so this person found time steps were not causing chaos there. Other people found that chaos went away when they dropped the time step. And nobody's really settled this issue back maybe 10 years ago. So when I was in Maryland, I met this guy, Wayne Hayes, who was really psyched about all this stuff. And he was integrating, he was a computer scientist working on these really high precision numerical integration techniques. And he had a big cluster, and he wanted to do experiments like this and answer the question. So what he did was he collected everybody's initial conditions, like all the people who've been doing those experiments I've been talking about. He said, give me your stuff, all your data, and I'm going to decide whether there's like little problems with your algorithms that are causing this behavior, or like maybe you messed up in your code. We're going to answer the question, because some of you are finding that it's chaotic and some of you are finding that it's not. So I mentioned that we know the positions of the planets to about 1 part in 10 million. It's really good. And Wayne, he's at UC Irvine. He did probably the most accurate numerical integrations that have ever been done, because we had this big computer back at Maryland, and he confirmed everybody's findings. Like, he got exactly what everybody else got, that some of the initial conditions were chaotic and some of them were not. So that's weird, right? Because it means that, so nobody's messed up. So what's left? Like, what could be causing that to be true? Does anybody have any ideas? Like, how could that have happened? Yeah.
Maybe it's chaotic in some dimensions, but not others.
Yeah. Good. So maybe it's chaotic when you put the planets here, and it's not chaotic when you put them there, but the difference between those two is within our known measurement certainty. So it could be either, basically. So that's right. And so when I first talked to Wayne, that's what he had decided was correct. And I said, well, we got to figure out what that looks like. Like, what do the manifolds, if you will, look like of the chaotic versus not states of this uncertainty ball in 30 dimensions? So we're going to figure that out. That was what we did. I'm going to show you the pictures. It's pretty awesome. So here's a pair of examples where we take Jupiter and move it by a meter from one location to another and do the sibling experiment for each position of Jupiter. Okay, so we move Uranus by a millimeter for each of them and see how quickly that perturbation grows. So in one case, it grows polynomially, no chaos. In the other case, it grows exponentially, chaos. And they're like really close to each other. Okay, cool. So we started making these pictures. The picture is going to show you red locations are going to be, like this one right here, is going to be a location of Jupiter where the sibling grew quickly, the sibling experiment grew chaotically, and blue is going to be a location of Jupiter where it doesn't. I guess you can't really see what, I got Uranus and Saturn here. And the units are in astronomical units, and the center is our best guess for where it is. But all of the states that you see here are plausible, like they're all within the known uncertainty of where the planets are. So, all right, so this picture says that blue means not chaotic, red means chaotic, and then there's these shapes. And each of the pixels takes about 3 hours to run on a computer, on a single machine, because you're integrating with time steps of days a 30-dimensional differential equation for 1 billion years. Okay, so this isn't good enough. We needed to resolve this better. And every time you cut it, now there's 4 more simulations to run, and 4 more simulations to run, 4 times as many simulations to run. Lots of time. So here's what it looks like. This is Lyapunov time, which is it's basically the inverse of the exponent. So if it's got a powerful Lyapunov exponent, the time's going to be short. It's a measure of how quickly this perturbation grows. Well, there's some structure here. Like, there's some states of where the planets are where you get chaotic behavior, and nearby, sort of off some low-dimensional state, it's very not chaotic and stable. Those states are stable. Every pixel on here, again, plausible state of where these 2 planets are, Uranus and Saturn. Lots of pairs of planets to look at. So here's Jupiter and Saturn. Again, some interesting structure. Look like these lines. Maybe they're planes or manifolds in this higher dimensional space that we're projecting down or we're slicing through. This is Jupiter and Uranus. Interesting, more structure. Regions up here like, oh my gosh, there's lots of chaos up here no matter what you do. Whereas over here, there's this really thin line. And if you go off that axis, stable. All the pixels are things that the solar system could be right now. Neptune and Jupiter. Got this big vertical stripe here. Neptune and Saturn. It's nuts over here. Neptune and Uranus, no chaos. Very interesting things happening. And one obvious question that we had at the time, all right, this is already like months worth of simulations. Well, what happens if we go and try and resolve a situation where we see chaotic red pixels right next to blue stable pixels. Like if we go in and zoom in on that, you don't want to take the screen in, right? What happens? Do we see that that continues to be the case? So here we take that thing, we've zoomed in on it, and now we're going to do the same experiment. We're going to like resolve this. Give me better data. Give me more pictures. So here now we're taking Jupiter and we're moving it by less than a meter now, like more like a few centimeters, and doing the millimeter experiment for Uranus. And we see that there are chaotic states, very structured chaotic states, right next to very stable states. That is the hallmark of this self-similar fractal structure that we've been talking about, where you try and you think you see a boundary and you go zoom in on it and you see more boundary. You see more, stuff that's doing one thing and stuff that's doing another thing, even though you were trying to zoom in on something that looked like a line. This is so cool. So I was at the time, like frothing at the mouth about this, and I happened to get a call from this guy Benoit Mandelbrot, who was trying to take this book that he had written, The Fractal Geometry of Nature, and sort of redo it with modern pictures and modern data. And I got to go talk to him about this at his apartment in Cambridge. And he was really psyched about these pictures. I was showing him this, and he hadn't heard that people were having this argument about whether the solar system was chaotic or not. And it turns out, it looks like the basin boundaries of chaos in the solar system are fractal. He was thrilled about it. It was really cool. He died a few years later, so I did not end up helping him get that book in shape again. I don't actually think it's come out since, but very cool opportunity. Very smart guy. We'll talk more about him after break. Okay. Questions about the pictures? I think I have, here's some examples together. I have a gratuitous movie because this is a high-dimensional thing that you'd like to be able to as you'd imagine when you stitch together these slices in this ball. I'm taking slices through this ball. You stitch them together, you see sort of things, where that's lots of red, you see that. So the answer to the question, by the way, is the solar system chaotic? Can you tell what the answer to the question is? We don't know. Like what we measure is somewhere in this ball, but the ball's got all kinds of interesting structure, and it's certainly there's large regions of blue where you can move around and see that everything nearby is stable. And maybe the JPL, as they get better measurements, we'll find that we're in one of those spots, or maybe we'll more likely, because this is what tends to happen in the world, we'll be near one of these boundaries. And we'll end up with a state that we can't tell whether or not it's chaotic or stable. So there's a paper about this if you want to know more about the details. It was a lot of fun. Questions?
Yeah, so with the weather, we gave this like a 14-day limit.
Yeah.
That we were able to only predict 14 days. And with the planets, clearly we can predict very, very well what's going on. So how far out can we predict currently? Accurately?
Yeah. What the planets are going to do.
What the planets are going to do, yeah.
As a closed system, really well, like millions of years. It's not closed. There's other things happening. There's asteroids coming in, and there's things that we can't see because they're not bright enough. I think that. So I don't know this literature like really well, but there's no concern at all that planets are going to collide or moons are going to. We're going to. Other things will happen first that humanity should be concerned about. Yeah. But there's very little money in NASA's budget to look for near-Earth objects that have a chance of colliding with Earth. Very little money. Like they've only mapped like 1% of these things because I'm making that number up, but a small amount of them. There's just not a lot of money. Yeah, so the question is it because it wouldn't matter because there's nothing they could do? I mean, they have all kinds of interesting ideas about how to handle situations like that, because often what will happen is they'll identify an object that's going to pass like 5 or 6 times before it hits, and so they'll come up with a way to gravitationally nudge it by a tiny little bit, which, as you know, is all you need to do. So they would, they might be able to go up and put something heavy next to it and park it there, and just that would be enough, if they could do it, to get it to be nowhere near colliding with the Earth. Other questions? Yeah.
So I just have a question on, because you were talking about how things usually in natural systems lie really close to those boundaries.
Yeah.
Why do natural systems tend to sit right on that boundary that even though you zoom in you can't differentiate?
Yeah.
Why don't they? Do some fall in clear as day areas that aren't chaotic?
So you've just asked one of the great questions in science, which is, why is there, it's called criticality. Why do the systems we observe often end up being on the boundary between order and chaos? And there are really smart people thinking about that question, much smarter than me. And I don't have a good answer for you. I don't think there is a good answer right now. I will say that evolution appears to produce those systems. So when you look, at the biological systems that people study on the Earth, they often are like that. And that was maybe kind of silly of me to imply my intuition would be that the same thing would be true for the solar system. There's no evidence of that, but it is what people see. And there's, so there's a class in the fall, Principles of Complex Systems, that is about trying to show you evidence of that. But it's an excellent question. Yeah, one of the open questions and the biggest ones in science in my mind. Yeah.
About the first animation of the Saturn flyby, how close was it to that moon?
They get, sometimes within tens of miles of the surface of the moons when they're going to go take a flyby. Yeah.
Follow-up question.
There's no atmosphere to worry about on those moons.
One of the moons of Saturn looks like a
Yeah.
Death Star?
Yes. I don't think that. I think that's a coincidence. The Death Star / Saturn moon. Yeah. Maybe if we get better pictures, we'll see that it is the Death Star. That would be scary. Okay, so I'm going to pivot big time and talk about zombies and hipsters. This is a fun project, largely led by Peter Dodds and a former master's student here and undergrad. So Cameron Harris, a really interesting guy, was a math and physics undergrad here at UVM in sort of maybe 8 or 9 years ago, and then did a master's degree here. He is now skiing all the time in Washington. He's sort of in an applied math PhD program studying the part of your brain that regulates breathing, but mostly he's skiing. This is at the University of Washington. So he does really interesting work with, I guess they're trying to figure out, when you breathe, there's a system you can regulate, but you can also forget about it and it works fine on its own in most people. But then in some people it doesn't work fine on their own and those people die. And they're trying to figure out why that system is resilient, but you can, they're doing a lot of mice stuff. And anyway, so I can tell you more about that if you're interested. But Cameron is, he's almost done with his PhD there, but he at the time was thinking about social contagion. So why is it that unbeknownst to you, you imitate your friends so much and, buy the same shoes and drink the same things and use the same words and imitate. Why do we imitate each other? There's lots of reasons why we do this, but we're trying to, so Peter Dodds has done a lot of work on models of this phenomenon. What it is about our interactions structurally that lead us to imitate each other. And this is an important topic, more and more so with the way we communicate information and news online. What is it that causes things to spread? Okay. So I'm going to tell you about a theoretical model of that spreading process that is inspired by sort of some simple models in complex systems, but that exhibits some really interesting behavior. Okay. And I'm just going to use Cameron's slides, which I'm going to flip through most of because this was his master's thesis presentation a while back. And okay, so yeah, lots of things. So this is often people, what they'll do when they're trying to understand how ideas and fads spread, how facial hair, how these things, how do these things get spread from one person to another, is they build models of how pathogens are shared from one person to another. Like somebody sneezes and then somebody walks by, and how things spread that way, as though that were sort of our best understanding for the way in which information would be transferred. Lots of problems with that. of course, especially with the way we're communicating online now. You don't have to be with somebody to hear what they have to say. And you also have lots of opportunities to get information outside of social networks. So if you want to study contagion on social networks, you have this big problem where not only are people connected because they happen to be alike in the first place, but there's also this world they walk around in that you don't observe, where other things could be influencing them. It makes it very hard to build models of social contagion. But so people often will start with this simple thing where we're just going to pretend that it's like we're sneezing on each other and getting colds. So Cameron was saying he doesn't think this is a good idea to think about social contagion in terms of the contagion of pathogens and the flu and what have you. So lots of these contagion models, you may have heard of this sort of susceptible, infected, removed situation where a person who hasn't been infected with something is considered susceptible, and then they have a rate of transition back to that state or to becoming infected, and then if they're infected, a recovery rate, or maybe they're removed from the population because they die. And then you set up a big network of these individuals and you seed an infection. You might do it on with geography as well. You might in building a big model of how you should vaccinate a population, you want to know should I go and do it in the schools first, or should we close the schools or close an airport? These are things you want to be able to model really well. But this is a very simple way of thinking about it. There's lots of people doing examples related to zombies, so that's funny. All right, and then the idea is there's got to be some sort of threshold function where you go from being in one state to another based on your neighbors. And this makes a lot of sense actually with respect to our behavior. So there's a study on Facebook not so long ago where people who were being told, oh, you could sign up for Facebook, it's really cool. They get an email inviting you to join. And in that email, some people just got the invitation and other people got pictures of the friends that who are having great lives on Facebook. Shouldn't you sign up? And they would toy with what pictures they show you. Should they show you your friends from high school? Should they show you one person from your high school and another person who's in your family and another person who's a friend of yours in college? And they actually found they could manipulate people by a factor of 2 to sign up just by showing you more diverse social universe contacts as opposed to everybody from one click. And so maybe you've signed up for Facebook, maybe you haven't, but you were probably a part of that experiment at some point. But this is something that people study. How do you influence people or how are people influenced by their little social network around them? Cool. But in the theoretical model, it's just you either are exhibiting the state or you're not. And then your neighbors have that same on or off. Are you on or off? Okay, so this concept has to do with networks, and there's maybe you've heard in mathematics of the idea of graph theory, but they're sort of the same idea. You have nodes, which in our case will represent individuals, and then links between them that represent some sort of contacts. Maybe they're friends, or maybe they work together, things like that. And this is a whole universe. There's another class on this, actually, that runs in the spring on complex networks. Very cool things. The number of links that are connected to a node is an important thing to measure about that node. So how many contacts you have. So there's work related to primates and chimps that says basically, and this has been confirmed with lots of evidence for us, that we really can only handle about 150 relationships. And this is called Dunbar's number, named after Robin Dunbar, who studies how we communicate with each other. And so our communications are very regular. When you go move to wherever you're going to start your life after you graduate from college, or maybe you'll stay here, the patterns of communication you have, even if there are new people coming in, will be pretty much the same. The amount of time you spend talking to your most trusted contact, and then your second, and then your third, these decay very regularly. And beyond 150, it's just very hard to maintain any meaningful communications with people. So it's been measured in lots of ways. So that's an example of a degree. So you might have sort of an inner circle of people you communicate with a lot, and then degree measures that. How many individuals do you have? And then there's a lot of theoretical work where you randomize all the links and then see what happens. What are the properties? Okay, contagion. Let's see. There's this idea of a response function. So how many people around you need to be doing something before you think it's a good idea to do it yourself? Or conversely, How many people need to be doing something before you think, oh, there's too many people doing this, I'm going to do the opposite? So this is your own individual response function to some behavior, and it probably varies in these different dimensions of your life, and it's incredibly powerful. It's also very hard to measure what your response function is. So how many people need to be, for example, telling you that this movie is incredible before you decide to go see it yourself? And does it help if they're people that you know very weakly, or are your best friends, or are people you never hear from? There's a lot of work showing that you are much more likely to get a job from people who you don't know very well, because everybody you know really well knows the same stuff as you. So there's lots of sort of interesting things about this, but this response function is important. How do we like query our neighborhood to decide what the social convention is? Yeah.
Is it possible, like, not to actually have a response, like the movie example? It's not that you would see it if your friends, or like they've just sold it so much that you don't want to see it.
Yeah.
But it's just at a time that's convenient for you.
The
And
movie
that's,
is.
like, yeah.
It's like it's at the time that you can go. Yeah.
And like it just pops up, and you're like, okay, without thinking of what your friends were saying
Yes.
about it. Or
Yep. Yeah, so your response function is like a little delta function based on time of showing, basically, is what you're describing. Yeah. So yeah, absolutely. So everybody's going to have a big mixture of this. And what we're going to have is a theoretical model where we got, hundreds of thousands or thousands of people, each with different response functions based on different things. And yours might have nothing to do with your neighbors. The model's going to assume it does have something to do with your neighbors, but you're right. That is an assumption. Yeah. Okay. Lots of contagion models. Peter Dodds has worked on this a lot. Fixies are a thing. All right, so how many people need to be riding a fixed gear bike before you think it's cool and you try? I've never tried riding a fixed gear bike. My son and I were riding up a big hill the other day, and he told me I had to stay in my hardest gear because he was trying to beat me, and it was really hard, and he did beat me. So that's a thing. All right, so here's an example of a response function. So this is called your on threshold and your off threshold. And what we're going to do is assume that people have something like this, where they're either exhibiting a behavior, that's a 1, or they're not. And it's based on something related to their neighbors. So they're going to query, the people connected to them. And maybe it takes, if your on threshold is very low, it only takes a couple people doing something for you to adopt that behavior. And the off threshold is when you decide, all right, I've had enough. Too many people are doing this. I'm leaving. Or for other reasons too. Like I got off Facebook in 2011 because I found it wasn't helpful to me, and my off threshold was pretty low for that. I also needed to study people on Twitter, and I thought I should use that. And so, anyway, so these are things that could be, you could decide on them. You could try and measure them. What are people's on and off thresholds? You could try and make them up and just see what happens. What we're going to do for this model that I'm going to tell you about is we're going to give a population of people randomly chosen, uniformly distributed on thresholds between 0 and 1/2, and also randomly chosen, uniformly distributed off thresholds between 0 and 1/2, or between 1/2 and 1. Getting at this idea. So there's imitation, that's the on threshold, and then aversion to conformity. We don't want to be like everybody else. That's the idea. Okay, so let's see. One cool thing is that when you average all of these thresholds together, you get the tent map. The on threshold and off threshold averages out to about roughly the tent map at the population level, and that's what we're going to be looking at individuals, but their average is the tent map. All right, I'm going to skip ahead to show you a couple things about what happens when we do this. All right, so you know about the tent map. We talked about that. Chaotic orbits are possible. We're going to take networks of size 10 to the 4, 10 to the 5. These are big networks of lots of nodes, and then we're going to impose on them some sort of average degree. So if you're all in this network, some of you are going to have a few friends, some of you are going to have lots of friends. People study this. Turns out there's this whole friendship paradox that your friends have more friends than you do on average. Just that's a statistical fact about the correlation between degree and friendship. And when we're going to do simulations, we're going to turn on a node. So I'll show you an example of one of these smaller ones. We're going to turn on a node. This is one of these. This actually only has 100 because it's very hard to visualize networks when they're more than 100 nodes. And then we're just going to count how many individuals are exhibiting a behavior. Now here, you're going to exhibit a behavior and you're going to not, and then you're going to do it again. But in practice, it's probably, like maybe beards are the only thing for which that happens. Like you grow a beard and then you don't, and then you grow a beard again. And some people just have a beard all the time. OK, so there's that person, that initial seed is going to infect other people based on these. They all have different on-off functions, response functions to the behavior. And what we're plotting here on the bottom right is the active fraction. So it's the number of individuals exhibiting that behavior. It's a fixed network, and people are connected to each other, and they're querying their neighbors. It looks sort of random. It's kind of hopping around. And now it's not. So what you'll see is that it has collapsed onto a periodic orbit. It looked chaotic for a while, but for that seed that we started with, and I guess you can see it's sort of repeating back and forth, but there are some that are going on and off every 4, and some that are going on and off every 2. And maybe there's one going on and off every 8. But that's a periodic state, and it's going to go like that forever. So you can stop when you see that happen. So that was with that initial seed. I could then take another node in this network and seed with that and see what happens. I'm not going to land in this same place. Turns out these basins of attraction are very weird in these high-dimensional networks. But I could do that for every single one of them in here and quantify what are the states that could be observed and average them out to get some sort of a bifurcation diagram value for this network. And then I could change how big the network is. I could change its average degree. Lots of different things to play around with. So let me show you a couple pictures. Cool. So here is, you've seen the bifurcation diagram for the tent map and the logistic map. This is iterating the polynomial cobweb, like the stuff we did in this class already. Over here are different responses that are observed in, now what's being varied is not the parameter, but rather how many people are connected to each other on average. So this axis is the average node degree. So that's the number of friends you query to decide whether to adopt a behavior or not. And there are 4 panels there based on different things that we might do. This bottom right one is the one that I was just describing, where we impose a network and we fix it and we seed an initial member. We would seed everybody and see what happens. These other ones, you could rewire the network every time step, or you could decide we're only going to query our neighbors every so often. We're not going to look every time step at what our neighbors are doing. We might wait 10 time steps before looking at our neighbors and have some distribution of that. So lots of things to play around with. But this is really cool. So we see the same sort of weird bifurcation diagram thing happening in this network space, where we're dialing, instead of the parameter, we're dialing how many friends you have. And there's some crazy thing that happens around 17 friends, where I just was showing you the video, where the behavior sort of collapses down into this lower dimensional stuff. And this dust that you see, the fact that this isn't some single point, that reflects the fact that different seeds, different initial members of the network that are turned on, result in different attractors at the end. The attractor being the active fraction that is settled down to the number of individuals going on average exhibiting this behavior. So here are some examples of the types of things that we see. This active fraction is that bottom right plot in the video that I was just talking about. So it often will bounce around for a while, not really sure what's going to happen, and then it'll collapse down. This looks like it's period 1, but really there's 1, 2, 3, 4. There's a period 8 orbit, I think. It looks like period 1 from the image. This looks like period 2. So does this. They're also slightly different. This is just for a single. This picture is just for a single network, and we're seeding the top 3 pictures. These are just different initial seeds that are turned on. So if you got 10,000, I think this was 10,000. So you got 10,000 nodes in the network. these top 3 panels are just 3 different initial individuals that were turned on. And then the question is, well, what happens as they, the behavior spreads around the network? And you can see that sometimes it collapses really quickly. This was after 1,500 iterates or so. And sometimes it takes a long time. This is 30,000 iterates it took. So the transient before things settle down is very different for different seeds. The only difference here is we're just turning on a different individual. Network is the same. It's fixed. Connections to everybody, all fixed. All right, so the collapse time, how long it takes to do that, is this sort of strange looking distribution here. You could see, so that one I think is one of the longer ones. So so around 30,000 iterates. And then there are these micro and macro periods that are really interesting. So the micro period is like if you look at what the period is in fact. So in our video example, this thing was repeating every 4, I think. This one's bouncing, I don't know, every 4. Yeah. So this one's repeating every 4. But if it kind of looks like period 2 because you get these 2 bands. So that's the micro period, the 4 in that case. And most of them have micro period 1. But then there are a bunch that are weird. There's in fact one that has a micro period of 60. So these are all just a different initial condition on the same network. All of these are the same network. We're seeding the different individual to start. And one of the simulations of those 10,000 has this repetition every 60 iterates. And then the macro period is, well, like, what does it look like from afar? So this looks like period 1 from afar. And that can be really weird. So what else to say about this? And this is just one network. This is a single realization of this 10,000. You could then just shuffle everything up and do another one, and you'd get potentially very different things. You could increase the size of the network. Lots of network behaviors, when you increase the size, the interesting things sort of resolve themselves and go away in the limit as everything gets more and more connected or bigger. But we see these really cool behaviors, and it being on a computer and there being a finite set of states to inhabit, it does need to settle down eventually into something, but it doesn't have to be of such low period. That's what's interesting about this. The basins of attraction of these states depend on the initial condition, which isn't the case for most of the stuff we've talked about so far. Pick any random initial condition, you get the same bifurcation diagram. Not so much the case here. Network movies. And then, so we can dial lots of different things. So in this video, we're going to dial the average degree and make a bifurcation diagram as a function of how often we tell neighbors about each other. It's either all the time out here at 1, or 3/4 of the time we tell neighbors about each other over here. As you increase the degree, you get these more and more interesting bifurcation diagrams. 2 parameters here: how connected are the networks? How often are you sampling your neighbors to decide what to do next? And so you get this 3-dimensional bifurcation diagram. I should have printed one out with a 3D printer and brought it in. Pretty awesome. It's like logistic map and then another, some weird little thing. Cool. But same type of stuff. You get these, periodic windows in there. Cool. Right. So what Cameron did for his thesis was work on the mathematics behind analytically trying to figure out what should happen for these networks. And that's what these pictures are. And then trying to visualize what they would look like on the computer. And he got really good agreement between the 2 of them. So very cool dynamical behavior. There's 2 papers about this, one that Dodds is the lead author on, and then one a few years later that Cameron was his master's thesis on this. And it's really interesting. So there's a lot of literature now about how we're connected and how we influence each other, but this is a fun example where you exhibit this, you see this exact same chaotic behavior that we see for the tent map or the logistic map, but it's in aggregate based on which individual gets turned on first. Chaos, networks, excellent buzzwords. Questions? Yeah?
So when you say it depends on the initial conditions, is that saying that some people are more influential than others, regardless of how, just because of their situation in the grid?
Yeah. So the question is, if the outcome changes based on which seed is turned on first, does that reflect how influential that individual is with respect to the group? And the answer is maybe. It could be the case that that individual happened to infect an influential person, or that that individual infected an individual who infected an influential person. This idea of influence is something that marketers try and measure. So you're a brand ambassador for Coke, and you want to pay somebody a lot of money to tweet or send Instagram pictures of yourself drinking Coke or whatever. And so they try and figure out who those people are based on properties of their social network, how many retweets they get, things like that. It's quite hard actually to seed something that spreads. People have done careful experiments measuring this on things like YouTube and how a YouTube view count takes off based on how it's being discussed online. And so there's a paper a few years ago showing that basically the stuff that doesn't really take off on YouTube but has a little bit of success, what happens is it spreads in an individual community very quickly and then dies because nobody outside of that community cares or understands it. Thinks it might be funny to everybody there, but so when you see something shared on your social network that you think's hilarious, but you share it with somebody who's like 10 years older than you and they don't get it at all, it dies there, right? So that's not viral. You hear the word viral used to describe something. That is not viral. If it spreads within the sort of the in-group and like quickly spreads but then stops, it's almost like a forest fire and there's a big firewall around you. It's really dry right here. Everybody loves it. It's gas. But then there's everybody else, either there's lots of water in the trees outside or there's a firewall. Things that do spread virally, I'm trying to think of the last time I saw something and I just thought, wow, it was the Dollar Shave Club commercial. Does anybody know about Dollar Shave Club? We're talking about beards a lot today. So there's a commercial maybe like 4 or 5 years ago that I saw and I thought everyone needs to see this right now. It's very funny. So things that spread really quickly don't spread quickly within an in-group, but rather, I was talking about your friend from high school, your mom, your somebody you met during the summer. You want to share this quickly with all of them, and then the same thing happens with them to all of their contacts. That's something spreading virally, and it is rare that you're able to seed something like that. It's usually that the thing being shared is amazing. Marketers want to be able to make like an ad for Coke do that, and you just can't because it's not something that regular people want to pass on to their friends. So I'm doing it right now. I'm telling you, you got to watch the Dollar Shave Club commercial from back in the day. I'll tweet it. Okay. Raise your hand if you've seen that commercial. You know what I'm talking about. All right. Okay. Yeah, it's rare that you see something that you're just like, oh, this is really funny. Okay. Did I answer your question? Kind of. Yeah. It's hard to know whether someone is an influencer because then, I was mentioning this, there's a lot happening outside of the network we can visualize. Like we don't know what you say on the phone to somebody about it or what you saw on TV or, the things we can observe are just your interactions that are on, basically text on the web. Yeah. So viral, you hear the word, oh, this is spreading virally. That really means it's going outside of these individual communities. And it is a thing, it's just very rare. And it's not something that can be imposed from the top down. The analogy that people like to use for that is that the system itself is like a dry forest, and it wouldn't really matter where the match is dropped. Like, it's going to burn. As opposed to the example I was describing where, there's this little region that's dry. Questions? Yeah?
It just makes me think of, so recently, that crazy right-wing dude, Yiannopoulos.
Yes.
How he all of a sudden got taken down by something that was information that has been out there.
Yes.
What was like the perfect sort of ingredients for this to
Yes.
happen?
Yes.
And how could that be replicated?
Yes. Yeah. So there's ample opportunity to apply the things I'm talking about to our political system right now and how we're getting information online and there are people trying to do that and trying to manipulate you and what you're going to do when you go vote next time. You know, Facebook, the stuff you see on Facebook is, there's another experiment that I didn't describe already, but where individuals who came to Facebook, this is back in 2010, and they've just replicated this for the 2012 election, but they were shown, you know, a little badge that said I voted, and you could click on this and say you voted that day, on the day of the election. 60 million people were shown this thing. And then some people were shown, you know, these are your friends who voted, and showed pictures of like your mom and your brother and your friend from high school, and pictures of people who had clicked on that button. And they could test then, you know, in the condition where you don't see this, the condition where you see it but there's no pictures, the condition where you have these different social universes weighing in on your, influencing your behavior, what happens? And going to voting records, they could see, first of all, did you click on the I voted button and actually vote? Because whether you voted or not, that's public, not who you voted for. And lots of people were influenced to click on the I voted button and then didn't vote, or had not voted when they clicked on it. So that's like a quarter of a million people had done that, I think, or even more. It was 1 million people did that. And then of the 60 million. And then there's what they were able to figure out using some statistics was basically that the people there were 250,000 people who went and voted that day in the US who would not have voted otherwise had they not seen this message. So think about that in the context of what role Facebook plays in your life and its ability to influence everything we do, in particular your decision to go vote. There's lots of evidence that when lots of people vote, it favors one particular party. Facebook is able to get lots of people to go out and vote by showing you this message. So there's a lot of power there that there's a lot of discussion going on now about how Facebook should be managing that influence they have. But scientifically, people are continuing to be able to show that we are easily manipulated without realizing it. And in that case, it was enough to get lots of people. It's a big thing. You got to leave. You can't watch TV. You have to walk outside. You have to go in a car or walk, drive to or walk to a polling place and then write down somebody, yes or no. There's a lot of things that are happening just because you saw this little picture. So that's just one example, but there's lots of other things that are happening. Yeah.
I feel like Facebook could easily predict who you're going to vote for also. It's kind of like a lot of power.
Yeah, absolutely. Yeah. There's the act of predicting who you're going to vote for, and then if they don't know if you're going to go vote, getting you to go vote. Or if you're undecided, showing you the information in the right way, like maybe you respond to fear better, or you respond to moral or value judgments better, and they can figure all that out from like 3 or 4 of your likes that you've done, things that you've clicked on that you like. It's incredible. Yeah.
People who didn't go vote that clicked the button, how much that was skewed by people who like I have a couple friends who have their name on Facebook that's different than their legal name, and how much that skews the data.
Very good.
Because they might have gone and voted, but obviously it's not going to show up if you have your last names being
good. Yeah. So that's something that they so the question is, well, what about friends who on Facebook don't use their real name, or it's some different version, it's a nickname or something like that? How would you tell if they voted? And they make some arguments about trying to estimate what that number is. And so that's a plus or minus in their estimate, and it's small. It's not the first or second digit. But it's a good thing to point out, yeah. Other questions? Yeah?
Any laws regulating how Facebook influences people?
Andrew's asked a good question. Are there laws about how Facebook is allowed to influence people? So when I do a research study at the university, and I'm going to influence somebody by showing them pictures that might make them sad or asking them questions about their life, I have to apply to something called the Institutional Review Board, who looks over the protocol of my study and makes sure that I'm not going to be endangering anyone's mental health, for example, or physical health. When you sign up for Facebook, you click somewhere, you agree to the terms of their service. That's the opportunity for you to vote that you don't want them to be able to do things to you. Unfortunately, that's it. You don't have any other control. There aren't laws about what they can do. It's just about money. So advertisers, if there's enough pressure, would stop using Facebook, for example. If they didn't like how the ads were being targeted at particular demographic groups or something, you could stop buying that product. That's a way that you can vote, but yeah, there are no laws. But this is, that's coming down the pike for sure. Okay, lots of exciting things. Office hours in 15 minutes back at Farrell. If you want, grab your homework and solutions on your way out. Thanks, everybody.